So for the second lecture today morning, we have Professor Michael Wolf, who will speak about ray structures on Teichmuller space.
Great. Thank you very much. So thanks for coming back. Okay, very brave. Or misread the schedule. I want to continue what I talked about last time, and this time spend more time on technique. And in some sense, I'll prove these theorems, or at least I'll create the illusion of plausibility, and I'll try to. And on the other hand, I mean, you want to watch a proof for an hour and 15 minutes, like that's a bit much. It's a bit much to give. So it's mostly a bunch of vignettes, and at some point I will stitch them together, and you can pay attention or not. Okay, so I'll remind you what we're talking about. I asserted this mental picture where there are Teichmuller rays, and then this is entirely in the setting of sort of conformal structures. Remember that we have the uniformization theorem, which says that conformal structures are relatable to hyperbolic structures once you solve a PDE, but you go back and forth. And Teichmuller space is alternately defined in from one point of view or the other, and part of the challenge is to move back and forth. And so on the conformal side, we had a variational problem which gave rise to Teichmuller maps, minimizing quasiconformal dilatation. And on the hyperbolic side, we had another variational problem, minimize Lipschitz stretch, which gave rise to a geometry on Teichmuller space of Thurston geodesics. Okay, and then we had something odd that was both conformal and hyperbolic, and that was a variational problem related to energy. And the solution to that problem were harmonic maps between surfaces, and they also and what I want to create the suspicion in you of, I mean, I'm going to say prove, is that these harmonic maps in some sense interpolate between these two points of view. And more precisely, the theorem is, and I think I wasn't clear enough about the convention that I was taking throughout the talk, which is my harmonic maps go from X to Y. X is the domain, Y is the range, and they are different in the sense, this is not a symmetric situation. It's asymmetric in that the domain only depends on the conformal structure. The range depends on the hyperbolic structure. So we had a back and forth that I didn't understand last time where why don't you change X and Y's, because I can't. Like X is squishy in this conformal structure, Y is rigid, this hyperbolic structure. Okay, and so there were two theorems. One was that so theorem one, I'll draw the picture here. What did I do? You fix the target Y. The Y is always to the upper right, the target. X is always to the bottom left, the domain. And you fix Y, and you let Xn go to infinity along some particular path, these harmonic map dual rays. And then you look at the harmonic map rays. You remember harmonic map rays? Maybe I need to say something about harmonic map rays. So for harmonic map rays, there was this Hopf differential. If I have F from X to Y, suppressing conformal to hyperbolic at my peril, this leads to this Hopf differential of F from X to Y, which was this quadratic differential, which you got by pulling back the metric on Y and then using the complex structure on X to decompose it. And you look at the non-conformal part of the pullback, and that's something holomorphic. It's something which would be written in local coordinates as Q is E dz squared. That's that Hopf differential. And there was a theorem that says that if you start with X and you look at that space of tensors of these quadratic differentials, but here's the quadratic differentials at X, that's meant to be drawn as some version of a tangent space or tensor space to connect it to X. And you look in this vector space at a ray, T times Q, what you, that determines a family of hyperbolic surfaces YT uniquely. And that's the basic homeomorphism. It is in some sense analogous to Teichmuller rays, where I would have exactly the same picture, except I would mean different things, right? I would mean conformal structures here. Here I mean hyperbolic structures. But same picture, a parameter, a vector space of tensors, and then that parametrizes a family of deformations. That somehow that rays are all related to each other in some way, in that their underlying directions of stretch are proportional. They're always the same underlying quadratic differential, the same underlying pair of foliations telling you how to stretch. Okay? All right. And so I look at these rays going through from xn to y, and they converge. And what I say they converge to is a Thurston geodesic through y. Alternatively, I can look, again, I have an x, I have a y, and this time I'll send y off to infinity, and I'll look at the dual rays. Guess I better send it off this way. And I look at the dual rays through that, and they converge to a Teichmuller geodesic. And so that's what I mean by this sort of interpolation. In some sense, if you like, this makes no sense, but it's a nice cartoon, I guess. I got the microphone. You start with a very degenerate situation with like y at infinity, and then you bring it, and that's a Teichmuller geodesic. You bring it back in, you get these harmonic map rays, then you let the domain go off to infinity, and the relevant rays become Thurston geodesics in the other direction. Okay, so that's the picture I want to somehow justify. Good. Let me, so the first topic I want to spend time on. Oh, do I? Yeah, let me see. Okay, are these dual rays? I think. Oh, that's right, I was gonna. Okay, and with lucky remember, how these were constructed, I'm going to look at the foliation. Here I'm drawing things on the universal cover. And the if I look at the leaf space, this is a measured foliation, which means that the sort of, if you're counting intersection number, I want to do it like that, then the intersection number is a homotopy invariant. You can just move it up and down. You can push that measure down, and you'll get something that is a tree. And the tree, I'm going to just draw something here on the space itself, which allows me, so you notice each point on what I'm drawing is touching exactly one leaf. And so I'm using that picture to really draw the tree, which I should really draw somewhere else. And so the piece of the tree looks like this. And then the fundamental group of the surface acts, or, I'm on the universal cover. So I watch this leaf, and it might go through a 0, which means that even though this point looked non-singular, really there was another branch. And that's just sort of true. That's true more or less everywhere. So this is a very furry tree. This is a real tree. Now, I bring this up now in the dual rays were, and this map, I'm sorry, one more thing I have to remind you of, is the map is Z goes to, drew it this way. Z goes to Y, which is harmonic. I just drew my horizontal foliation somewhat vertically. I will regret that, but if everyone could just turn your head. All right, but this is the map. And so what I described last time is I had a pair of harmonic maps, x tilde go to y tilde cross t, and this was, each one was harmonic, so so the pair of them is harmonic, and this has been carefully rigged so that this is not just harmonic, but conformal. And what I asserted last time is that harmonic plus conformal is the same thing in this setting as being area minimal. Okay. All right, now, I drew this picture where I had the tree here. It's related to some quadratic differential. In fact, it's related to the horizontal foliation of the quadratic differential. I have the target y tilde, and sitting inside here, I have the graph x tilde, and that's really talking about the relationship of all three objects in one picture. And the harmonic map dual ray was this is a metric space, so I'll emphasize this is a metric R tree. And the way the scaling works is if I put a t here to scale that metric, if I demand that x stays fixed, then the y's will start to change. And that's the harmonic map ray. This was the harmonic map ray. And there was a dual ray, which starts with the exact same picture. PQH, Y. And in this case, I will scale the tree. I will fix Y, and so X will have to change. Great. I bring all this up again because A, I think it's somewhat unfamiliar, and I'm going to use it a bit, so I wanted just to dwell on it. And I want to linger a little bit on this. I'm going to go spend some time on this and convince you that, in fact, you already believe the second statement. So the second statement is going to come from things you already know from Teichmuller theory in some sense, as understood through this picture. I did forget one thing last time. Forgot one item from last time. And, I'm told to pander to the students here, which, usually students know far more than everybody else, but so I'll be didactic. So, I defined this object on the Riemann surface. And I say, this is an interesting object. But if I say, and I have an interesting object from the point of view of Teichmuller space, it has to have two interpretations. One is at the level of the surface, and one is at the level of the deformation space. You have to have both, or it's not interesting, or you don't know something. So that's a model. And so the point is that, how do I think of this object in terms of Teichmuller theory? Well, so how to think of the Hopf differential in terms of Teich theory. It works like this. Now fix the conformal structure X. Then for Y in the Teichmuller space, measure the energy of Y, by which I mean the energy of the harmonic map from X to Y. This is then, if you like, thinking of this as a function, this is a function on Teichmuller space, a real valued function. You plug in a point in Teichmuller space and read off the energy. So I have a function on Teichmuller space. Okay, that's interesting. Now I have to do function theory. So as soon as I take, if someone hands you a function, what's the first thing you do is you look at the derivative. So what's this derivative of the energy? This is a covector. This depends on X. So I look at the derivative of this energy at X, at Y. So it depends on X. I look at the derivative at Y because that's the variable. And what I will get is a covector back on X. And what this covector is minus, I'm going to get this wrong, but the real part of the Hopf differential from X to Y. So here's Teichmuller space. X is in the bottom left, Y is in the top right. I think about how much Y varies. Think about Y varying. And the way I would look at this is back here on X, there's some tensor, which is its differential of this energy. And that's going to be what, and that will say how the energy changes as I change Y. It's a covector. Okay. One more fact about this. So how do people use this? Often, it's often used this way, and at the end of the talk, it's often used this way, and I bring this up because I'll bring it up again, is that, if you look at the energy as a function on Teichmuller space to R, and Teichmuller space of S. And this is often proper. In other words, as you leave all compact sets, so what do I mean by that? I mean that if Y goes to infinity, then the energy, say X to Y, also goes to infinity. So this function blows up as you leave compact sets. So you have a real valued function on this cell, which is going to infinity. So that means it has a minimum. And if it has a minimum, that means that at that minimum, the differential at the min is 0. But the differential at the min I just told you is the Hopf differential from X to X min. And then you check that what the Hopf differential is the non-conformal part. So the non-conformal part of the pullback of this min, probably should have been Y. So how non-conformal is this harmonic map to the min? It's not. Because I pulled back, I looked at this 2-0 part, which is measuring the non-conformality, and I found out that it's 0 because it was the critical point of something on Teichmuller space. So, ping-ponging between the view of the map, between thinking of what's going on in the deformation space in terms of function theory on the deformation space, and thinking about what's going on the surface in terms of the map, I find out that this map at this critical point on Teichmuller space is completely not conformal. So it's conformal, and now I've found a conformal map. Yeah. Oh, I hate it when you do that because it never is. well, it's a cotangent vector of the, it's a covector, right. You pull things back to like space on X and you're parametrizing through X. It's a way to think of it. Oh, no, you're right. I completely screwed this up. I was bothered while I was doing it. I completely screwed it up. You're absolutely right. You fix Y. You start yeah, I was writing this and I'm thinking, something's wrong here, but it's in my notes. So, you know, you start thinking about how X moves here. And so that's, yeah, thank you very much. How did I screw this up? So, so this is really, I've only known this for 40 years. So, so I look at the differential at X with a fixed Y. So is the hop from this F, thank you, I messed it up. Okay. Yeah. Okay, I was looking at it. It didn't make, usually the notes are right? So you keep going and you like realize what was bothering you later, but all right. So, great. So I have this different, yeah. So it's the gradient changing X with a fixed Y. I have this Y out there and Y can be anything. I put it in Teichmuller space. It could be a three manifold. It could be anything, a harmonic map to anything, and you're varying over surface domains. Thank you. Okay. Forget all that and restart. What's, Sarah, should I say it again? Let's do the whole thing again. Yeah, well, let's start over. I have energy from X to Y. To look at a map on Teichmuller space. So now let's forget Y. Let's just go to some target N. Okay. And now let X move around from to N. Okay, just various probes, take X for each surface, look at the harmonic map into N, and look at the energy from X into N. Fixing N. Okay, and later on, N will be Y. So to be very general, let me move it out of this setting. Should have just erased everything. So I will get the energy, and I think, well, what happens to the energy if I start moving in my domain? I try different domains. And the energy is a function on Teichmuller space. So its derivative is a covector on Teichmuller space at the point where I'm doing deformations. And the statement is that that derivative, you know, so that abstract object on Teichmuller space is realized on the surface as this tensor. So that's the moving from the deformation space down to spaces of tensors on the surface. Okay. And then this part's correct. But yeah, so this is hop from X min to N, and then I'll find a conformal map. So you can imagine you have a negatively curved three manifold and you're looking for a minimal surface. In some sense, this is pretty close to the way Jesse Douglas solved the plateau problem in 29 or 30, got the fields of metal in 36, was by looking at maps to three space, which solved a boundary value problem. And he looked at the energy of disks with given boundary values parametrized. That's a proper map. He found that therefore it had a minimum. And because it had a minimum, its gradient was 0 at the minimum. And so that provided for a conformal harmonic map at the minimum. I have lied a bit about the parameterization. But this is really goes back at least to Jesse Douglas, if not Dirichlet. Jesse Douglas. Okay. All right. Can I reset the clock because I screwed up? You don't get these mulligans. Okay. So that was an element I messed up, and I messed it up twice. Back to this picture. So I want to linger a little bit on this minimal graph notion, because I assert you are actually very familiar with this. So take a quadratic differential. Jean-Marc, thank you for saving me. Take a quadratic differential, say phi, on a Riemann surface. And then on that Riemann surface, I think people are familiar with this, right? We talked about it. You have a pair of foliations. Let's make them really look singular. And something like this, right? And I can have a pair then of dual trees, dual to this horizontal one, which I've now drawn horizontally in blue. I have some tree, the horizontal one from Q, and I have this other tree down, which would be the tree vertical. And we can work out what these are. I think you could sort of see that this tree looks like this, and this tree, you could sort of, oops, don't want to use that color. Don't have too many colors here. I'm doing the red tree, so I have to have some red leaves. And you can see, that's should be probably something like this. Do you see that as the leaf space? So I have a red tree like this, okay? And I have a pair of harmonic maps projecting along the vertical or projecting along the horizontal to these trees. Each one, this map is, Z goes to X. This map is Z goes to Y. Both are harmonic. And now I have Z going to X comma Y. That's conform. I have XY going to XY. That's conformal. So you see the conformal harmonic map here, right? And so this is, so anyway, it's evidently a conformal harmonic map. Okay? The Hopf differentials of each map are negatives of each other when you compute it. And that would mean that the sum of the two Hopf differentials is 0, and being 0, that would mean that the Hopf differential is 0, so the map is conformal. It has no non-conformal part. Okay. Great. What does a Teichmuller ray do? What a Teichmuller ray does is it multiplies this tree, the way I set it up, by T, right? So now I have a scaled tree, and I'll have scaled foliations. I'm not going to get fill in all the details, and so and an underlying Riemann surface. So if this underlying Riemann surface is X, this underlying Riemann surface is XT, and I have still a pair. So I've changed the Riemann surface. I've changed the quadratic differential in a corresponding way by changing the maps to the trees. So a Teichmuller ray is obtained by taking harmonic maps to trees, scaling the trees, and looking for the conformal map to the product of the trees after scaling one. That's a Teichmuller map. No, I'm going to do this. I'm going to scale the tree. Okay, then I'm going to look for a harmonic map somewhere. I'm going to find a good conformal harmonic map whose projections are each harmonic. That surface, which I might find through this sort of process, right, will give me a new surface and a differential on that surface and maps to the trees whose pairs of Hopf differentials are balanced in the sense they sum to 0. And now I have a Riemann surface and a quadratic differential. And so this is the sort of the harmonic maps tree version of Teichmuller's of a Teichmuller array. So I'm saying all I'm doing is translating into this language of what you know about Teichmuller arrays. Okay? Great. Right, so maybe I'll just, so I'll summarize a little bit. So we find the Teichmuller array by finding a minimum of the energy from we look for a surface to t times QH cross T times plain old QV. So this is now my N for the target. I find a minimum. I find a surface which minimizes this energy, and that will be XT. And we can read off the pairs of we can read off the Hopf differential from that and find the Teichmuller differential. Okay? Always fun to show you something you really understood and now in a way where you can't understand it. But anyway, that's but this is useful. Okay, great. Remember this, I'm coming back to it a little bit. Yeah. All right. Yeah, so let's find a Teichmuller array. Okay. You have two trees you're starting with. So you're starting with a quadratic differential. You want to do a Teichmuller array, so you want to find a teeth surface and a teeth quadratic differential. And you know secretly that the teeth quadratic differential is some version of affine stretch of the original one. Okay. So fine, just start with these two metric spaces. Take this metric space, scale it. Look at the product. It's a singular space, but it's a perfectly good metric space product. There's enough theory around to say I can measure the energy of maps to that, and I can look for the very best Riemann surface that I would map into that product and have the least energy. When I find that least energy Riemann, when I find the Riemann surface which has the least energy, I'll have some surface XT. And then I'll have two harmonic maps. I know a priori that the Hopf differential is 0. I know a priori what the maps are because these things have to be giving the leaf spaces. When the dust settles, you'll find that you found the pullbacks, the level sets of each tree will fit together to give you a quadratic differential on that Riemann surface XT. Okay. I got one more board. Okay, so now let me talk about some other elements of the proof. So this is what I mean by, so here's a vignette, right? Now I do something else. So So why do we get stretch maps in the limit? All right. This has to do with, so I'm thinking about maps, for example, like for this, x to yn, where yn is really far out in Teichmuller space. So the geometry of yn is very different from the geometry of x. It takes a lot of energy to get from x to yn. Arbitrarily large energy. The energy function is actually proper. I'm not proving that. But so it turns out that, well, and I've already told you that we're talking about quadratic differentials t times q, so the hop from x to say yt on array is yt is defined, so this is a large number times a quadratic differential on x. Okay, so here's x. It has some divisor, or the quadratic differential has some divisor, but if you want to think of this on the scale of t times q, it's really big. In the scale. So what I mean to say is that, we have these leaves. I'm going to think of the foliations, like maybe I have singularities like this. They're really far apart. And in between, I have regions where, if this is, z dz squared locally, then this is just plain old dz squared. From the point of view of a point here, those zeros are extremely far away. So if you think about like convergence of the geometric topology near here, I'm really thinking about harmonic, this harmonic map is going to think that it is the harmonic map. So, so f from xt to y, from x to yt, near, if you don't mind, this point w, by which I mean far away from the zeros, is approximately like some map u from C to, let's just put yt into H2 with Hopf differential dz squared. Locally, this looks like dz squared. If you take a geometric limit of the surface with the Hopf differential based at w, everything blows away from the w, and you're just left with the plane and dz squared. Okay? Sarah, you're the interrogator, and you're just staring at me, so I know that I didn't do that. I didn't communicate that. Are you having trouble seeing? Oh, okay. All right, can you see this part? I see the picture's all I need. Stare at this point. Let t go to infinity. As t goes to infinity, all this stuff out here and all this stuff out here just flies away. And what this looks like, so this is going to converge to C at the point W, and with the quadratic differential, you'll see it's just plain old dz squared. And I'm mapping, somewhere into H2, so I'll still be mapping somewhere into H2. So this invites the question, what do you know about harmonic maps that have Hopf from the plane into H2 that have Hopf differential dz squared? So, I've been talking about these harmonic maps, I'm trying to puff myself up here and say, oh, I'm solving this system of PDEs, and isn't that really hard? But it's actually not. You actually know lots of harmonic maps. So the very simplest harmonic map that anybody knows, I think, well, one of the simplest, is you can think about maps from C to H2. So what's an example of a harmonic map from C to H2? And you don't even need to know anything about harmonicity to guess this, since it's a natural quantity. So here's one, map C, I'll start with Z, and you map C to R by taking Z to X. That's harmonic, right? Better be. And then follow that up by going to some geodesic and just parametrizing the geodesic by arcway. So I start with the plane, I go down to the line by just projecting in the vertical direction. So and so I'll just get a blue line here as the leaf space, and then that gets mapped into some geodesic. And so I'm following up a harmonic map with something which is totally geodesic. That better be harmonic, and it is. What's the Hopf differential for this map? Well, I don't know, but it better be translation invariant. And you can either compute it, or you can realize, look, it has to be translation invariant because everything in sight is. So this is the Hopf differential of this is a multiple of dz squared. And okay, and so that's the example. So what do we learn from this? We know that this little region is becoming like the harmonic. So the harmonic map from X to YT, because the quadratic differential is blowing up, its behavior, its geometry decouples into regions around, say, the first one will be regions where there's no zeros. And in that case, what this map will do is it will take these horizontal leaves and it will send them to geodesics. So this whole region here, all these lines are going to go to a single geodesic, or nearly so. So they will. So we've learned part of what this map does at high energy. So at high energy, this is a projection of this big region to near a geodesic. What about the rest of the map? I've trapped myself. I have to go back. So this was one example. So now what do we know about, let's say, z cubed dz squared? Well, its picture has 5 prongs. And so here, once again, I'm going to think about being on the plane. Okay, why do I think about being on the plane? Because for the same reason, if you look in the geometric topology at the map based at the 0, everything else flies away. And what you just have left is a single high order 0. So what's the harmonic map? So now I'm asking, what is the harmonic map from C to H2 with Hopf differential z cubed dz squared? Well, so I'm mapping over to H2. And the point is that if I look very, very far away from the 0, once again, it's going to look like dz squared. So very, very far away, this map is going to look like a geodesic. And very far away over here, it's going to look like a geodesic. And as you make your way around, there's something I'm brushing under the rug about how you pass from geodesic to geodesic. There's this notion of a Stokes line, but I'll not get too far. I'll not get into that. That's a fascinating but different story. The point is, what you get is an ideal polygon as the image. But we now know then what this high energy harmonic map looks like. Because this portion, so let me get some colors. So over here, I'll draw it down here. Well, no, I'll draw it over here. Here, I'm going to get some sort of ideal triangle. Then, as I pass through this field, I'm going to get a bunch of geodesics, which are all very close to the edge because this and this are the same. Then down here, I'm going to get another ideal triangle. And over here, I'll draw it with cube. I'll get some ideal pentagon, with these sort of geodesics in between. And so that's what the map will look like. It has very large diameter. So if I rescale this, so let's divide by t to the half, turns out to be right. Divide the entire picture by t to the half. This is hyperbolic objects. You divide them, so they have a finite delta radius. You divide them by t, they shrink. And what you're left with, by the way, is a tree. So what you see is that these high energy harmonic maps, properly normalized, are becoming harmonic maps to a tree. No, well, I'm taking this picture, and this quadratic differential has size t, so everything was really large, and I wanted to rescale. Well, my energies were really large, so if I want something of finite energy, I scale by t to the half, I'll get something of finite energy, but when I scale the target by t to the half, I'll have to end up with a tree. So again, this is all happening on the surface, so if you wish to, so you have to ask what's going on in Teichmuller space, and what is going on in Teichmuller space is the dual to, no, it's, no, I will use the word dual, but I don't think it's the answer to your question. So I have an ideal triangle. Scale the ideal triangle by t to the half, by some really large number. It becomes so you scale it and this ideal triangle becomes, like this, right? I don't know if you can see it, but I made it really small in the center and put these things close together. And in the limit, you get a tree. So the Teichmuller picture then is this. You have X here, again, made tensor space, TQ, you have this ray, YT, and what is happening is you're converging to the tree dual to the vertical foliation. Okay, so this is really the sort of harmonic maps point of view of the Thurston compactification. So this is in boundary TH. Like of S. Okay. Great, that's a very old result. So why do I tell you all this? Well, it's sort of fun, but also at this point, you now believe statement 2. Why do you believe statement 2? Okay, so why statement 2? Well, statement 2 talked about harmonic map rays. Okay, and I had this picture where I have TQ. Let me make sure I get this right. Yes. T times the tree with the horizontal foliation, and then sitting in here was X, right, conformal. And remember, this was the harmonic map rays. I scale the tree, I keep the domain fixed, and the Y had to change. But now we know, what does Y do? It goes to the vertical tree for. So what is X becoming? It's the conformal map to the product of trees. But you've already decided that was sort of the central part of a Teichmuller ray. If I were to somehow scale this also by an S, then I would get in here some family XS, and those would just be the Teichmuller rays. So, okay, so that's the picture. That's why this is true. In other words, these target domains become more and more tree-like, and so the harmonic map, which is the conformal harmonic map to the product of Y with the tree, becomes more like a harmonic map to the product of trees, and a harmonic map to the product of trees, you endured me showing you, is the same as a Teichmuller. There's a couple aspects. And there's something I'd really better say. I'd really like to put this under the rug, but it invites a problem. Something really important in all this, in this picture, was that I fixed my domain X, and the quadratic differentials got large. So when I took limits, I could stare at like a thick part of the surface and say that's going to C. If I had a varying family of surfaces, I couldn't do that. Like, what if there was like what if this is developing a really small collar or a really small curve through there? I wouldn't be able to do this sort of talking about convergence. So there is, so the first part is, I'll just say control of degenerating Riemann surfaces and quadratic differentials in Yair Minsky's thesis. And so what he does is he finds a good region with controlled geometry. It's really remarkable. Outside of which these estimates, like the ones around dz squared going to geodesics, boom. So he very carefully will, he'll cut out some polygon around here and some polygon around there. But then if there's bad portions of the surface, he'll extend this sort of polygon through, and he'll find a well-tailored region with well-tailored geometry on which these estimates work. Okay? And that's really important because we're letting our domains degenerate. So in order to play any of these games, I need to have control as to what happens when the domains degenerate. This is a basic ingredient. Okay. To say this properly, It's really quite a long statement, and I'm just going to say we can, nicely done. All right, towards uniqueness. Well, this is, I'm changing my talk on the fly. Here's a background fact. Here's something I know. And I will remind you about the theory of Jenkins-Sarin. I think this is 1966. Okay. And they're interested in minimal surfaces over minimal surfaces in Euclidean 3 space over a checkerboard, over a square. Okay, so the picture is this. And so, and really, you know, what I'm talking about is this, shoot, I didn't write down. I think it's famous, it's just surface of Schwarz. Schwarz's second surface. I may be wrong about that. And the point is this, suppose you have a checkerboard in the plane. Let's see if we can draw this well. Yeah, I'm in the plane. And maybe you've seen these pictures. And you have, you're looking at cylinders over this checkerboard. And there are these minimal surfaces that kind of look like this. They swoop on down, they cling to, say, the east and west sides, and they come down from being asymptotic to the east and west sides, and then they turn, and then they become asymptotic to the north and south sides. Okay, so you know they come like this, and then they turn, they do that, and they're actually periodic across the lines. And so what Jenkins and Sarin considered in generality is the asymptotic boundary value problem for minimal surfaces where, so some sides will go to infinity and some sides will go to minus infinity. So solve that problem. And so, so what Jenkins and Sarin proved was existence and uniqueness. With some conditions, particularly uniqueness. Okay? So that's a background fact. You can solve this sort of infinite plateau problem. Okay, so what are we doing? Shirk, thank you. Right, and so Shirk, this I actually know, proved the existence of these surfaces in 1834 in Krella's journal. I know that because I had to, I proved some, I actually created, with Matthias Weber, we have some generalizations of these, which we submitted to Krella's journal, and we started with, in a previous paper in this journal, anyway, or something like that. So, okay, so what do we have? So again, you know, I have the same picture, I have a Y here, I have an X here, and I have a scaled tree. Okay, and so now scale the tree. So I'm interested in minimal surfaces in some setting like this. So what's the scaled tree look like? Well, the scaled tree, when you know, it used to be like, you know, something like that. If I scale it, the tree is going to have like infinite prongs. All the other stuff will float away to infinity in some sense, at least locally. So in studying minimal surfaces in this product, I am led to study minimal surfaces with infinite boundary values in something that looks like a domain surface and an infinite tree. It's kind of like R. So we could prove uniqueness is proved adapting techniques from Jenkins-Sarin, from the Jenkins-Sarin theory. Since Jenkins-Sarin, there's been many proofs of that result. We picked out one that was particularly amenable to generalization. And so that's the uniqueness of the minimal surfaces. And that uniqueness is what will get translated into convergence. In other words, we'll take a bunch of limits, we'll take a subsequential limit, we'll get some limits, but every subsequential limit will yield a minimal surface into the same object, but it'll be unique by the minimality, so therefore everything converged. That's the point. Yeah, I know. No. Let's see. I am interested in, so I'm looking at maps through Y. Y is fixed in this. So in this picture, Y is fixed. I scale xt, I scale t, okay? And I look at some family xt going to infinity, and I want to study xt somewhat. I'm interested in convert. And so I'm studying this minimal surface. And limits of that. So yes, I'll end up with a limiting minimal surface, which would be, you're pushing me to say things I don't want to say, but I'll end up with I'll be looking at a minimal map from a noded surface into this setting where I have an infinite tree. Yeah, I will try. This is just the first half of the talk, right? I'll assemble the piece. I have a plan to assemble the pieces later. So, but there's some uniqueness that comes from the minimality. Okay, so let me just say what the basic proof outline is here. Do I want to write it? So, sorry, I thought I had one more thing to say, but I don't. I did it already. All right, so I want, so we're looking for, want convergence to Thurston geodesics as xt goes to infinity along a dual ray, right? Thurston geodesics through Y. Okay. So first, there's some basic compactness that I haven't told you about, but it's not so bad, which gives subsequential limits. Then of the maps of, I have a sequence of harmonic maps. I take some, I will end up with a limiting Riemann surface with punctures, a noted Riemann surface, and a limiting meromorphic quadratic differential on that surface subsequentially. Compactness subsequential limits to some x infinity and some q infinity, which this is meromorphic. Energy is infinite. I'm going to have to get something infinite. So these limits are then unique by some version of this argument. Okay. Now, what do we know about the limits? So, but the limits are a little odd. The limits harken back to work of Subhojoy, because I now have some surface with nodes and meromorphic Hopf differential data. So, and we've already, so the same sort of like understanding of these pictures says what the images of this are. So these images are, oh geez, I won't be able to draw this like you do, Subhojoy. So they are crowned surfaces. So they have surfaces that way out here, the images are going to be geodesic boundaries. So these are crowned. And so I have another one over here. And, and now I have to fit them together. Okay, so it's getting technical, but I have 6 minutes left, so I can talk to myself and pretend I've talked to you. So the point is that the resulting maps to crown surfaces may be fit together using, in some sense, lingering data of the approximating sequence. Okay, that's really vague. But what I mean is this. This guy used to look like this. I mean, it's approximated by something. And, I have this vertical foliation. It was orange, red? It was red. There's a vertical foliation which was running between the pieces. Now, alas, it has broken apart. And so, not really sure what to do, but there's enough here, and we do some analysis here and here to show how sticky it is that I actually know the recipe to put things together. And once we put things together, so these fit together. That's kind of so that's some version of the argument. What I wanted to highlight is, so there's a few key elements. The space that the harmonic maps decouple into ways that you can, into portions that you can analyze piece by piece. And they are very simple. Translating things into this language of minimality lets you access all sorts of things about minimality. That's a sociological statement. The math statement is it changes a parametric problem. So harmonic maps are parametric in the sense that you say where one point goes, right? It's a map from one manifold into another into an intrinsic problem. Intrinsic problems are different. If you look at Jean Marc's lectures, the hard parts are uniqueness, often. So we get uniqueness. Once you have uniqueness, that's a wedge. And then you scramble around for a bit and use uniqueness to get convergence. Okay. Oh, shoot. 3 minutes. I have to tell you, I won't be able to tell you applications. Applications are to the envelope. But I have to tell you, I said that one of the key points of all this is that there are unique, what am I going to erase? I told you that there's unique harmonic stretch lines, so corollary or so. There exists unique harmonic stretch line Thurston geodesics. So for all pairs X, Y in Teichmuller space. Now these are all WZ. These are hyperbolic surfaces. There's a unique harmonic stretch line Thurston geodesics from W to Z. Okay. How does this work? So the way it works is this. So here's W, here's Z, as usual, we're in Teichmuller space. And now I look at a function on Teichmuller space. So I'm going to look at a function FR, which is look at the energy to W minus R times the energy to Z. It's an energy function. And when R is small enough, for R, and let's see, I didn't write it down. For R less than, say, the Lipschitz constant from W to Z, up to some power I didn't write down. Sorry, but it's something I know. This is proper. FR is proper. So that says that there is a minimum of FR, minimum, say XR of FR. Well, if it's a minimum, then the gradient of FR at dFR at this minimum is 0. So that's the same as dE at this XR minus R dE at XR to Z. But this is, yes, I heard you. But so this is, of course, the Hopf differential from XR to W, and this is the Hopf differential from XR to Z. So we find that the two Hopf differentials differ by a scalar. So that means there's this XR here, and W and Z are on the ray through XR. I now let R go to the relevant Lipschitz constant. This goes off to infinity, and this ray converges to a Thurston geodesic. I have enough control of about XR to invoke the previous theory. So that gives the canonical Thurston geodesic between any pair of points. And the argument is exactly like the one I screwed up earlier. Okay.
What is the Lipschitz constant?
Sorry?
What does the Lipschitz
mean? Let's see, when you look at, because you want to say you're proper, so you stretch, so you're like, one energy is less than another because of like the stretch squared. In other words, I look at, I'm unprepared for the question a bit, but if it's the bar room song that it would sound like would be, you look at the maps to one of them, you then scale by the Lipschitz map to the other one, that's a competitor for the harmonic map, but the harmonic map has less energy, and that gives you properness. Okay. Okay, alas, I'm out of time. So this this does have applications. Using these uniqueness, I can talk about and out of time, that doesn't mean I'm going to stop. But anyway, so, I look at the envelope from X to Y, and using this uniqueness and using something about what I know about the Lipschitz if I go along here and I have a W, no, the point is, along this harmonic stretch lines, I know that within the envelope, the stretch lamination, the optimal stretch lamination remains the same as the original lamination until it stops. And it stops exactly on the edge of the envelope. And that allows me to parameterize the envelope in terms of, in some sense, as a cone over a cone. All right, that's it. Sorry. Thank you very much for your attention and patience.
Questions?
The last picture? Yeah. Yes. And that's me. And that's me.
Yeah. So in this envelope, one of the domain, in order to get your result, one of the domain was diverging.
No.
Oh, so
You missed, you blinked when I did this whole passage. Okay. This very fast statement says that you hand me any pair and I can find a unique Thurston geodesic from between those 2 points. There may be many Thurston geodesics, but there is a unique one which comes from this harmonic situation, And so I'm going to use that one. And once I have a canonical Thurston, so I'm picking out from the envelope through the 2.5 hours of talk, my favorite Thurston geodesic, which exists and is unique between any pair. Once I have that, I can put it to work. And it fits well within the study of an envelope because for that is something separate to prove, which I'm not telling anything about, that it's not so hard. It's like gymnastics with definitions, really. There's no estimates or anything, really. While you stay within the envelope, the optimal stretch, when you look you look from X to Y, you look from W to Y, and that doesn't change until some moment when it does. And that moment is the boundary of the envelope.
okay, yeah. So what you are saying is that you use the uniqueness that you proved before to characterize the envelope for any 2 points.
Right. I mean, it's really, there's a very hard line between these two.
Mm-hmm.
This is paper 1, this is paper 2. But this was a corollary of the main theorem that I didn't write when I stated those theorems. You don't want to do that till he tells you to. That's the question. When do we get lunch?
So these theorems 1 and 2, so am I right in understanding if you just want subconvergence, then you can allow any degeneration like this? And like
Yeah.
xn's go to infinity in any way you want?
Any. Let's say most, and then I'll reflect. We have a theorem that says you get subsequential convergence. I forget, in general cases, I forget what the hypotheses are.
Both of these situations.
At least, I think both. I think both. Still recording? So,
I'll have to look.
Does the construction also give the best slip snap from W to Z, a natural one, a unique one?
Yes.
Does give you a canonical one.
Yeah, I mean, the sort of behind the whole theory. So he asked, does the construction give a canonical best Lipschitz map? And yes. So, I mean, the point is, well, so, the Thurston ones are when you have, when you have a lamination, so when say your maximal stretch lamination has complementary regions of just ideal triangles, but it's silent when you have something that's more complicated. And so what we're doing is picking out some Thurston stretch lamination, the Thurston geodesic, which where in a setting where this optimal, where the maximal stretch lamination is not maximal in the sense of having ideal triangles as complementary regions. And there's other people who have done that. Athanase has stuff, I think, and Athanase and a collaborator, I'm sorry, and Calderon and Farr have ways. I mean, there's a number, and yeah, I messed this up, and I apologize to the people I'm leaving off the list.
Any further questions? Let's thank.